How many horsepower does a 1000 CFM fan need? That question is missing the load.
Motor sizing starts with the fan duty point, passes through fan and drive efficiency, then finishes at the motor nameplate and actual electrical supply.
Let's run one complete example. Our illustrative duty point is 1000 CFM at 2 inches of water static pressure. The fan curve shows 60% static efficiency at that point.
For inch-pound units, required fan shaft horsepower is airflow times static pressure, divided by 6,356 times fan static efficiency. 1000 times 2, divided by 6,356 times 0.6, equals 0.524 horsepower at the fan shaft.
If this is direct drive, there is no belt loss between motor and wheel. For a 90% efficient belt drive, divide 0.524 by 0.9. The motor must provide about 0.582 horsepower. The next candidate is 3/4 horsepower. Still check peak brake horsepower across the permitted fan curve, startup torque, ambient conditions, control range, and the manufacturer's allowance. Do not depend on service factor for normal overload unless the application documents allow it. Motor horsepower is rated mechanical output at the shaft, not electrical input. 3/4 horsepower equals about 0.56 kilowatts of output because 1 horsepower is 0.746 kilowatts. Input power is higher because the motor has losses. A 560 watt output rating is not 560 watts at the panel. Next, match the supply socket. Record actual system voltage, phase, and frequency. Then match the nameplate combination and the wiring diagram.
A common North American 480-volt distribution system may feed a motor rated 460 volts, but compatibility must still follow the motor manufacturer's allowed range and project code. A 230/460-volt dual-voltage motor requires the correct lead connection. Never move jumpers from memory. Frequency also matters because it changes synchronous speed and can change other ratings. Now look at full load amps, or FLA. FLA is the current the motor is designed to draw at rated load, rated voltage, and rated frequency. It is not locked rotor current, service factor amps, or the current at today's partial load. For an induction motor, an engineering estimate for 3-phase input current is output watts divided by square root of 3 times voltage, efficiency, and power factor. With illustrative values 0.75 horsepower, 460 volts, 82% efficiency, and 0.72 power factor, the estimate is about 1.19 amps. But that estimate does not replace the nameplate. Suppose our sample nameplate states 1.4 FLA. Use the actual marked value and applicable electrical code and manufacturer instructions when selecting conductors, overload protection, short circuit and ground fault protection, disconnect, starter, and variable frequency drive. Those devices do not all use one current rule. This is a selection workflow, not a branch circuit prescription. Starting current is a separate event. Across-the-line induction motors can draw several times running current while accelerating. The locked rotor code, load inertia, fan torque, acceleration time, starter, and supply stiffness affect whether the motor starts cleanly. Do not solve nuisance trips by increasing protection blindly. Confirm the start method and protection coordination with a qualified electrical professional. EC fans need a different drawer in the sizing bench. This real Longwell GCB 250 EEC 99 specification identifies 115 VSE, 50/60 Hz, 420 watts maximum input, and 3.7 amps maximum input, plus separate power and control leads. Because the motor and electronic controller are integrated, use the product's declared input ratings, wiring diagram, protection requirements, and control interface. Do not force an EC assembly into an induction motor FLA table. Other nameplate fields prevent mechanical and thermal mismatch: RPM, frame, enclosure or IP rating, duty, ambient, insulation, rotation, bearings, and drive compatibility. With a VFD, confirm inverter duty, speed range, low-speed cooling, cable/filter requirements, and drive output current, not horsepower alone. Before fieldwork, de-energize exposed live parts whenever required, apply the site's lockout and tagout procedure, and have a qualified person verify the de-energized condition with suitable test equipment.
Then commission the fan at the intended system condition. Record voltage, current on each phase, rotation, speed, vibration, temperature, airflow, and pressure. Current below nameplate FLA does not by itself prove correct airflow, and balanced airflow does not excuse phase current imbalance. Your final motor selection card should contain the fan duty point and peak brake horsepower, drive type and efficiency, selected motor output, voltage, phase, frequency, FLA, starting method, speed, enclosure, duty, ambient, control method, protection basis, and commissioning plan. Send that card and the fan curve to Longwell for a model-specific review. The goal is not a bigger motor, it is the correct motor and electrical interface for the real fan load.